We shall now resume for the next talk. I am Pierre Arnoux from the University of Aix-Marseille, and I have the great pleasure to introduce the next speaker. So our next speaker is Carlos Gustavo Moreira, who is better known as Gugu. He is an eminent member of the vibrant mathematical Brazilian community. Gugu is from Rio de Janeiro, where he developed an early taste for mathematics, going on to get the golden medals at the International Mathematical Olympiad in 1990. He graduated that same year at the University Federal do Rio de Janeiro, and he continued to master and PhD at IMPA in Rio, where he obtained his PhD in 1993 with Jacob Pallis as his advisor. After a postdoc at Orsay University in Paris, he became researcher at IMPA. Gugu works at the confluence of dynamical system, number theory, and combinatorics. He is particularly interested in the transition from simple and well-understood dynamical behaviors to complicated dynamics when there is a perturbation, and with its relation with a fractal dimension of invariant sets and with number theory. He collaborated with many mathematicians, notably with Jean-Christophe Joukos, who had a great influence on him. He is a member of the Brazilian Academy of Science, of the Third World Academy of Science. He received several prizes, including the Homoclinic Prize in 2009 and the Third World Academy of Science Prize in 2010, and he recently received the Erdős Prize of the World Federation of National Mathematics Competition for his work in the diffusion of mathematics as coordinator of the Commission of Mathematical Olympiads of the Brazilian Society of Mathematics and IMPA, which organize the Brazilian Mathematical Olympiads. Gugu has many interests in society outside of mathematics, and this presentation would not be complete if I did not mention that he is, among other things, the president of the Cultural Association José Marti of Friendship between Brazil and Cuba, that he is a very good connoisseur of samba. He is a strong supporter of the Flamingo team, and he has more than 5,000 recorded goals, some of which can be seen on internet. Gugu, the floor is yours.
Thank you. Thank you very much. Esse aqui, gente. O laser eu posso pegar e apontar. Tá bem, tá bom. So, thank you very much, Pierre. Very nice introduction. So, first of all, I would like to thank the Scientific Program Committee for the invitation, which is, of course, a great honor for me. I also would like to thank my Brazilian colleagues for coming. Thank you very much. So in Brazil, we have built a solid and growing mathematical community thanks to the effort of many people in the whole country, and also to some heroes, as Maurício Peixoto, Elon Lages Lima, Manfredo do Carmo, and my advisor, Jacob Pallis. So I would also like to thank my foreign colleagues for coming. So thank you very much for coming. Your presence is very important for our mathematical community. And I hope that in the next time you come, and I hope you come back soon, you will find a democratic country. So thank you very much. And so we start to talk on dynamical systems and dynamical bifurcation and fractal geometry. So this talk will have two parts. And in the middle, I will start talking about Diophantine approximation, and then I'll try to make the relation between these two fields, so establish. So I will start with. Yeah, it works. So, sorry. Okay, good. So, we start talking about dynamical systems. So, dynamical systems is concerned with asymptotic behavior of systems. It gives model for many phenomena in natural sciences. Poincaré is considered to be the founder of the modern theory of dynamical systems. He worked a lot on the three-body problem in celestial mechanics, and he introduced some fundamental theories, some fundamental aspects of the theory of dynamical systems. He started the qualitative theory of differential equations. Also, he somewhat started ergodic theory. For instance, has this famous Poincaré recurrence lemma. So here we'll talk mainly about two kinds of dynamical systems. So the dynamics of transformations. So we will iterate functions, and so we have a function from a space to itself, usually a finite dimensional manifold, and we consider iterations of this function. So orbits of points in X. So we take a point X in the space, and then take X, f square of X, etc., and we try to understand the behavior of typical orbits for typical systems. We also consider flows, typically given by solutions of autonomous ODEs, or ordinary differential equations, in manifolds of finite dimension. And there are two usual goals of dynamical systems. Try to describe most orbits in most systems. This is a very difficult task, but in many situations we are able to describe the system. Also to characterize dynamical behaviors which are persistent, which are robust. So I thought about Poincaré, and there was a very important development of theory of dynamical systems in the 30s by Andronov and Pontryagin, who introduced the notion of structural stability and classified structurally stable flows in the plane, and also to my colleague Maurício Peixoto, who in the 50s showed that typical flows in dimension 2 in orientable surfaces are structurally stable. Then still we have an important class of structurally stable systems, the Moxes-Mayo systems, which exist in any manifold and are structurally stable, as proved by Jacob in his PhD thesis in low dimensions, and then by Jacob with Steve Mayo in general. And then we move to the notion of hyperbolic systems, which is a larger class of stable systems. It was introduced by Steve Mayo in the 60s, after an important global example by Anosov of a structurally stable diffeomorphism of the two torus, which has dense orbits and infinitely many periodic orbits of all periods. So this example, so to x plus y mod 1 in the two torus, and of the famous horseshoe introduced by Zmeyo. So Zmeyo horseshoe is like this. So we take, say, a square or a rectangle, we contract in the horizontal direction, expand in the vertical direction, and make it turn like a horseshoe and comes back to intersect the rectangle. And the maximal invariant set, so there is a set of points such that all iterates, forward and backward, always remain in the square, which has a nice geometrical structure. It looks like the Cartesian product of two Cantor sets. It contains infinitely many periodic orbits of all periods. The periodic orbits are dense, but also dense orbits in the set. So it's kind of much more complicated dynamics than the previous examples. But it's also a robust object. So this kind of behavior is persistent under small perturbations. So we have the general notion of a compact invariant subset. So it's a subset which is compact invariant, and the dynamics contracts in one direction and expands in a complementary direction. So we have this global behavior. And this this kind of behavior is persistent under small perturbations. So it was introduced in the 60s, and this is a very important notion in dynamics. Say that a diffeomorphism, for instance, is hyperbolic if its limit set is hyperbolic. So it's a set of omega limits of orbits. Okay. So there is this famous stability conjecture by Palles and Smale, which says that essentially the structurally stable systems are the hyperbolic ones. Indeed, the axiom A ones, there are some conditions on transversality, but essentially the hyperbolic ones. And this conjecture was proved by Magnier, a great Uruguayan mathematician who worked at IMPA, made his PhD with Jacoto, and he proved this conjecture in the C1 topology after fundamental contributions by many people, by Nosov, Smale, Jacot itself, Wellington de Mello, my colleague Robin and Robinson. So, but it's still open in the CK topology for k larger than 1, and then also proved by Hayashi for flow. So there are extra technical difficulties for flows, and only in 97, in this paper of 97, Hayashi proved the conjecture is still in the C1 topology for flows. This conjecture is still open in higher topologies, as I said. And we'll talk a lot about homoclinic bifurcations. Homoclinic bifurcations is perhaps the most important mechanism that creates complicated dynamical systems from simple ones. I'll try to explain why and give some reasons for this statement. I begin quoting Poincaré itself, who realized the existence of homoclinic intersection, homoclinic phenomena, when he studied this three-body problem in celestial mechanics. So this is a famous statement by Poincaré that the behavior of systems with transversal homoclinic intersections is very complicated, and gives a general idea of the complication of the three-body problem, and in general of all problems in dynamics which involve this kind of homoclinic orbits. So the first natural problem related to homoclinic bifurcations is the study of homoclinic explosions in surfaces. We consider a one-parameter family of diffeomorphisms of a surface, which is uniformly hyperbolic, so structurally stable for negative values of the parameter. And for m equal to 0, it presents a quadratic homoclinic tangency associated to a hyperbolic periodic point, which may belong to a Hochschuh, or maybe an isolated periodic point. And then the tangency unfolds. I will show a picture in the next slide. So it unfolds for positive values of m and create transverse intersections between stable and unstable manifolds of the periodic point. So a main question is what happens typically for small positive values of the parameter. So this is a picture of m equal to 0, so of the moment of the first tangency. You have a first homoclinic tangency in this picture associated to a Hochschuh. So we have this blue Hochschuh. Have this, in blue we have the unstable lamination of the Hochschuh, and in red we have the stable lamination of the Hochschuh, and we create a first homoclinic tangency between a stable and an unstable leaf, and it unfolds for positive values of m. So this is the picture for positive values of m. And for positive values of m, perhaps we create new tangencies between the stable and unstable leaves of the Hochschuh. Perhaps for some parameters we have new tangencies, for other parameters no. And it's very important to understand whether we really create new tangencies or not, because homoclinic tangencies is a well-known obstruction for hyperbolicity. Hyperbolic systems cannot have homoclinic tangencies. And, well, the situation, as I said, the horseshoe looks like the Cartesian product of two Cantor sets. And in the moment of the tangency, the situation is like we have two Cantor, we have this line in the middle, which is called a line of tangencies. So it's a set of points where we could have some tangency between a stable and unstable leaf. We can extend the foliations to differentiable foliations in an open set, and then we have like a line of tangencies where the extended foliations are tangent. But we intersect this line of tangencies with the stable and unstable laminations. We get two Cantor sets that in the beginning, they touch by their end points. So we have just one point of intersection. For negative values of mi, they have empty intersection. They have a first intersection for mi equal to 0. And then these Cantor sets move in this line. In the first approximation, one of the Cantor sets is fixed and the other one moves with constant speed. Of course, in reality, it's not exactly that, but it's a good approximation. Then we have one Cantor set like that, and the other moves with constant speed. We have a lot of values of parameters for which they have new intersections, and when you have a new intersection, you have another homoclinic tangency. But there can be values of parameters such that the intersection is empty, and then we have some hope of having hyperbolicity. And it's an important question to decide whether the set of values of parameters for which these two Cantor sets have non-empty intersection is small or large in the parameter line. So let's move to this conjecture of Jacob-Pallis now, which is in the direction of this statement I did, that homoclinic tangents are perhaps the most important mechanism from passing from simple dynamical systems to complicated ones. So Pallis' conjecture in dimension 2 says that any diffeomorphism can be approximated either by a hyperbolic system, which is stable and well understood, or by a system presenting homoclinic tangency. And, well, this conjecture was proved in C1 topology by Enrique Pujals and Martin Sambarino, who are here. And Jacob also has a general version, an arbitrary dimension of this conjecture, where we need to add heteroclinic cycles, which is a new phenomenon. So as a cycle given by intersections of stable and unstable manifolds of different indexes, so also a non-transverse cycle. And, well, and the general version is that any diffeomorphism can be approximated either by a diffeomorphism presenting a homoclinic tangency or by a diffeomorphism presenting a heteroclinic cycle or by a hyperbolic one. And there is a major advance in the C1 topology for this conjecture by Sylvain Covizier and Enrique Pujals, who proved that essentially the conjecture, the only thing is that instead of proving that the system is hyperbolic in this case, so we may approximate either by a homoclinic tangency or by a heteroclinic cycle or by an essentially hyperbolic diffeomorphism, which means that the diffeomorphism has a finite number of hyperbolic attractors which attract almost every point, which attract an open and dense set of points in the manifold. And there's perhaps a little complement to understand, but it almost proved the conjecture. Of course, all these conjectures are still open in the CK topology for k larger than 1. So this is related to the closing lemma and to some famous problem in dynamics in higher topologies. So homoclinic tangencies are ubiquitous, appear everywhere in some sense, close to the non-hyperbolic systems. On the other hand, homoclinic tangencies provoke the existence of complicated dynamical phenomena. And I will show just two results in this direction. There are these classical works by Sheldon Newhouse, of which I will talk more in next slides, who showed that after any homoclinic bifurcation, so close to any homoclinic tangency, there are open sets of persistent homoclinic tangencies, that we cannot destroy by small perturbations. And this provoked, under a hypothesis of dissipativity, for a residual set in this open set, diffeomorphisms with infinitely many sinks, which means that the dynamics is very, very complicated and difficult to describe. So he develops new concepts in fractal geometry that, together with the already established hyperbolic theory, gives proofs for this result. So this indicates that after a homoclinic bifurcation, we have very complicated dynamics. And also this famous work by Leonardo Moura and Marcelo Viana, who are here, in which they show that after a homoclinic bifurcation in dimension 2, we have the creation of Renon-like strange attractors with positive measure in the parameter set. So this is also, so there are very rich and complicated dynamics being created after a homoclinic bifurcation. And so homoclinic bifurcation is a powerful mechanism which creates complicated dynamics. And so, okay, so I try to convince you that homoclinic tangents are perhaps at least an important mechanism to pass from a well-understood dynamics to complicated dynamics. And okay, so let's talk a little about fractal geometry and fractal sets. Fractal sets appear naturally in dynamical systems in many situations. And the notion of fractal dimensions is very important when you try to understand fractals and to measure fractals in some sense. So the most important fractal notion of fractal dimension is the house of dimension. So this is a short definition of the house of dimension of a metric space X. We consider covering of X by small balls, and we measure the coverings by taking sums of the radius of the balls to some power, and the right power, in some sense, is the house of dimension. So it's a natural tool to measure fractal sets, as regular Cantor sets, which I will mention shortly, and to compare different fractal sets, which usually have zero Lebesgue measure, but may have very different sizes in a meaningful sense. So house dimension is very useful to measure and to compare fractals. Now I talk about regular Cantor sets, which is a very important object in order to understand, for instance, homoclinic bifurcations in the plane. So regular Cantor set is a one-dimensional hyperbolic set. So it's a set in the real line, which is the maximal invariant by an expanding system, by a system of expanding maps in some union of intervals. And usually the regular Cantor sets have some kind of self-similar property. So small parts of regular Cantor sets are diffeomorphic to the whole set, or at least to large parts of the set with bounded distortion. So small parts of the set look like the whole set. So the most popular Cantor set is the usual Ternary Cantor set, the set of numbers in 0, 1, in whose representation in basis 3 there appear only digits 0 and 2. And this is a regular Cantor set defined, for instance, by this expanding map, which is 3x between 0 and 1/3, and 3x minus 2 between 2/3 and 1. And the maximal invariant of this in the interval 0, 1 by this function, so the set of points for which we may iterate this function infinitely many times and stay always in the domain of definition, because the interval 1/3 to 2/3 is not in the domain of this function. So if some iterate gets in this interval 1/3 to 2/3, then the point is not in the Cantor set. But the points such that we iterate the functions, for instance, the points between 1/9 and 2/9, if we apply the function, we get directly in the interval 1/3 to 2/3, where the function is not defined. So 1/9 to 9 is outside the Cantor set. So, okay, and a key question for regular Cantor sets is when you have a pair of regular Cantor sets, is to decide whether or not the arithmetic difference of these two Cantor sets has or not non-empty interior. I will talk more on arithmetic difference. I'll define precisely what means the arithmetic difference of two Cantor sets. But this is an important question both in dynamical systems, in the study of dynamical bifurcations, and also in number theory, more precisely in Diophantine approximations. It's a subject that I will also discuss. So a horseshoe is in dimension 2. As I said, looks like the Cartesian product of regular Cantor sets in a precise sense. It's indeed diffeomorphic to the Cartesian product of two regular Cantor sets, which are called the stable and the unstable Cantor sets of the horseshoe, which are given by intersections of the horseshoe with local stable and local unstable manifolds of points of the horseshoe. And in particular, this implies that the house of dimension of the horseshoe is the sum of the house of dimensions of the stable and the unstable Cantor sets. And the value of this house of dimension plays an important role in this bifurcation theory, so in the study of homoclinic bifurcations associated to such a horseshoe. As I will say, we see it shortly. And so the first theorem, some important result on homoclinic bifurcations related to fractal geometry is due to Jacob and to Flores-Takens. And they proved that, they proved about 83, but it was published in 87 in Annals. The theorem says that if you consider a homoclinic explosion, so a first homoclinic bifurcation as before, associated to a small horseshoe, to a horseshoe which has house of dimension smaller than 1, the house of dimension of a horseshoe in a surface can be any number between 0 and 2. So here the hypothesis is that this dimension is smaller than 1, so in the first half of this interval. So the dimension is small. Then we have full Lebesgue density of hyperbolicity. So for most small values of the parameter, the corresponding system is uniformly hyperbolic. So this is the theorem by Pallis and Takens. And a central geometric fact used in the proof is that the arithmetic difference of two regular Cantor sets, in this case we will apply this to the stable and the unstable Cantor sets of the horseshoe. So the arithmetic difference of the two Cantor sets is a small set, is a set of 0 Lebesgue measure, indeed of house of dimension smaller than 1, if the sum of the house of dimension of these two sets is smaller than 1. So what is the arithmetic difference? For instance, I have these two sets, K1 and K2. The arithmetic difference is the set of all differences, x minus y, where x is in K1 and y is in K2. But it also can be interpreted as the set of values of the parameter. So if you consider one of the sets fixed, say K1, and the other set moving with constant speed, so you take K2 plus t, K2 is moving with constant speed. The set of values of t for which K1 intersects K2 plus t is precisely the arithmetic difference, because you need to have x in K1, y in K2, such that x equal to y plus t, so t is x minus y. So the set of all these values, x minus y, is precisely the set of values of the parameter for which they intersect. And the set is small when the sum of the dimensions of the Cantor sets is small. particularly in the situation of the theorem by Pallis and Takens, where the sum of the dimensions of the stable and unstable Cantor sets is smaller than 1. On the other hand, if the sum of the dimensions is larger than 1, this is no longer true. For instance, we have this classical Marstrand's theorem, which says that if you take a set in the plane with dimension larger than 1, then almost every projection on the real line will have positive Lebesgue measure. If you apply this to the Cartesian product of K1 and K2, you conclude that for almost every lambda, the arithmetic difference K1 minus lambda K2, so we put a scale in K2, for almost every lambda, K1 minus K2 has positive Lebesgue measure, provided the sum of the house of dimensions of K1 and K2 is larger than 1. Okay, so this is Marstrand's theorem. And so this inspired Jacob to make this conjecture on arithmetic sums, arithmetic differences of regular Cantor sets. The conjecture says that typically, if the sum of the house of dimensions of two regular Cantor sets is larger than 1, then typically the arithmetic difference will have non-empty interior. So not only positive measure, but non-empty interior, which is important in the study of homoclinic bifurcations, because non-empty interior means that for all small translations, you still have non-empty intersection. But indeed, you may have more than this, as we'll see in a moment. But Jacob was interested in also, of course, in Neuhaus' theorem, so what did Neuhaus? Neuhaus introduced a new kind of fractal invariant, the thickness of a Cantor set, which I'll not define here, but he proved that if the Cantor sets are very thick, has large values of this new fractal invariant, then the arithmetic difference is an interval, or perhaps a finite union of intervals, but there are many situations of stable intersections that we cannot destroy, not only by small translations of the Cantor sets, but by any small perturbation of the Cantor sets, even involving perturbing the dynamics which define the Cantor sets. So he gave a condition which is open and guarantees stable intersection. So Neuhaus used this to exhibit these open sets of diffeomorphisms with persistent homoclinic tangencies and where residually there are diffeos with infinitely many sinks. And after every homoclinic bifurcations, you may find small open sets in the parameter line contained in this Neuhaus region, so corresponding to persistent tangencies and residually presenting this phenomenon of infinitely many sinks. So now, talk about Jean-Christophe. So I did my PhD with Jacob, and then I did a postdoc with Jean-Christophe Yokos, and where we proved a strong version of Pallis' conjecture. So here there is a photo of my friend Jean-Christophe. It was a great mathematician which left us too early. So let me describe this work with Yokos. So we proved that typically when the sum of the house of dimensions of two Cantor sets is larger than 1, their arithmetic difference typically contains intervals persistently. So not only for this pair of Cantor sets, but for any small perturbation. And, well, indeed, we proved a stronger result. It depends on this notion of stable intersection. So two regular Cantor sets have stable intersection if any small perturbation of them have still non-empty intersections. Small perturbations, we may apply diffeomorphism close to the identity, but we also may perturb a little bit the dynamics which define, so the expanding dynamics which define the Cantor sets. And so this is just a definition, and we prove that stable intersections are typical when the sum of the dimension is larger than 1. So if you consider this set omega of pairs of regular Cantor sets, such that the sum of their Hausdorff dimension is larger than 1. Then there is a large open set U, open and dense set U contained in omega, such that if you have a pair of Cantor sets in the set U, then indeed for every non-zero value of lambda, there are translations of lambda K2 which have stable intersections with K1. And more than that, the set of these translations is dense in the arithmetic difference, which is the set of translations which have non-empty intersection, is dense in the boundary, so the set difference between the arithmetic difference and the set of stable intersections has 0 Lebesgue measure, and indeed the Hausdorff dimension is smaller than 1. So almost every position of intersection is a position of stable intersection in this case, for typical pairs of Cantor sets with dimension larger, such that the sum of the dimension is larger than 1. Okay, moreover, we proved that U is a very large set in the sense that the complement omega minus U has infinite codimension. So typical families with a finite number of parameters whose image is contained in omega indeed has image contained in U, completely contained in U. And we also may change in the statement stable intersection by D stable intersection for any D between 0 and the sum of the dimensions minus 1. D stable means that the intersection has Hausdorff dimension at least D in a persistent way. So any small perturbations will have, the intersection will have at least Hausdorff dimension D. So the intersection will be somewhat large, will contain a Cantor set with positive Hausdorff dimension. So, okay. There are some main techniques in the proof of this theorem related to the existence of a recurrent compact set of relative positions of limit geometries of the Cantor set. So there is a criteria, dynamical combinatorial criterion, which guarantees stable intersection. So we prove this. So this is perhaps the main technical lemma of the paper, is the scale recurrence lemma, which is a lemma which guarantees the existence of a recurrent compact set at the level of scales. So we are not, for the scale recurrence lemma, we are not interested in translations just in the relative scale of the two Cantor sets. And so this is a smaller space where there is always a compact recurrent set. I have no time to make very precise definitions. But after the scale recurrence lemma, we apply a probabilistic method. We do not, so we have two Cantor sets with sum of dimensions larger than 1. We do not construct explicit perturbations which have stable intersection. Instead, we consider a family of perturbations with a large number of parameters, and we prove that for most perturbations in this family, so for most parameters, the corresponding perturbations indeed have stable intersection. So it's like Herd's probabilistic method in combinatorics and in many areas, where we show the existence of some objects without constructing them explicitly. Instead, we construct a probabilistic space, and we prove that with positive probability, the objects you want indeed exist. So, okay. So these techniques, so we applied this theorem also in the original context of homoclinic bifurcations. We proved that in a homoclinic bifurcation associated to a horseshoe with dimension larger than 1, associated to a large horseshoe, indeed we have positive Lebesgue density of persistent tangencies, so of Neuhaus phenomena. And we still have in this context positive density of hyperbolicity, but not full density. So these two things may coexist, but the union of hyperbolicity with persistent tangencies has full Lebesgue density at m equal to 0 in this case. Of course, there are open sets where we have tangencies all the time after the bifurcations. So H may be empty in some examples, but there are some other open examples in this context where these two phenomena coexist. So, okay. So generalizations of these techniques and of these ideas gave rise of many different results. For instance, in the beginning of 2000 with Jacob and Marcelo, we extended these results on first homoclinic bifurcations, so on homoclinic explosions, to arbitrary ambient dimensions, so we have analogous results. With Jorge Eric Lopez Velasquez, we proved this so the theorem with Jacob may be regarded as a theorem on projections of Cartesian products of two regular Cantor sets, and here we extended this for projections of Cartesian products of several regular Cantor sets, so in arbitrary dimensions. Collaboration with Zulu, Wellington Silva, also a former student of mine. We studied horseshoes in higher dimensions. The geometry of horseshoes in higher dimensions is much more complicated than in dimension 2. But we proved, for instance, that horseshoes such that some stable Cantor sets have house of dimension larger than 1 are what are called blenders. So typical projections of these stable Cantor sets will contain intervals persistently, but have a lot of other results on typical geometry of horseshoes in arbitrary dimensions. So with Alex Samudio and Hugo Araújo, who are also former students of mine, we are extending this theory to, so some parts of the theory were already fully extended and some others still need some results, but we have a program to extend all this theory to complex Cantor sets, to conformal complex Cantor sets. We aim also to understand homoclinic bifurcations in complex dimension 2 instead of real dimension 2. So we have some progress in this direction. So now I will start, in principle, a completely different subject. I will begin talking about Diophantine approximations, so approximations of real numbers by rational numbers. I will start with the simplest and most fundamental problems in the subject. So it's like it will look like we will start again a completely different subject, but we will see in a while why these two subjects are related. So there are a deep relation between these subjects. And so we'll start with this, as I said, the most fundamental problem in Diophantine approximation, which is related to approximate real numbers, so say irrational numbers, by rational numbers. And what we expect from the best rational approximations of a given irrational number. And there is this classical theorem by Dirichlet that given an irrational number alpha, we always have infinitely many rational approximations such that the error of the approximation is smaller than the inverse of the square of the denominator. So this inequality always has infinitely many rational solutions. And this can be improved, can be slightly improved. So Hurwitz and Markov showed that we can put a square root of 5 multiplying the denominator. So this inequality, alpha minus p over q, is smaller than 1 over the square root of 5 times q squared, also has infinitely many rational solutions for any given irrational number alpha. But square root of 5 is the largest constant for which this result is true for all irrational numbers at the same time. So let's see. But on the other hand, for particular values of alpha, we could expect to have larger constants in this statement. So this is what is given by Dirichlet's theorem. Every rational numbers can be approximated by infinitely many rationals, which are smaller than 1 over q squared. So Hurwitz-Markov puts this square root of 5 there. So this also always has infinitely many rational solutions for any given irrational number alpha. But in general, we can look for the best constant k, which works for alpha, not for every irrational number, but for the given irrational number alpha. Indeed, we may define this function k of alpha. K of alpha is the supremum of all this constant k, such that this inequality, alpha minus p over q, is smaller than 1 over kq squared, has infinitely many rational solutions. This can be given by this formula below. As we saw by Hurwitz-Markov theorem, k of alpha is always at least square root of 5. Indeed, for the golden mean, it is square root of 5. So for the golden mean, we cannot improve this theorem. But for other real numbers, we may expect to have larger constants. Indeed, we may look to the image of this function. So the set of values of k of alpha for all irrational numbers is called the Lagrange spectrum. I should say that k of alpha can be infinite. So for some values of alpha, this inequality can have solutions for all positive values of k. In this case, k of alpha will be infinite. And well, indeed, this holds for most real numbers, for a set of full Lebesgue measure. But still, there is a set of full Hausdorff dimension, the Hausdorff dimension 1, the set of badly approximate numbers, which coincides with the set of numbers with bounded continued fractions, bounded coefficients in the continued fraction, as I will see, for which k of alpha is finite, and then the image of this function k of alpha in this set is called the Lagrange spectrum. So Hurwitz's Markov theorem says essentially that square root of 5 is the smallest element of this set. So understanding this set, so if you understand well this set, you understand a lot of results in Diophantine approximations, and it turns out to be a very interesting set from the geometric or from the topological point of view. It's a complicated set, as you will see, in which encodes many Diophantine properties of real numbers. So the first important result on the Lagrange spectrum is due to Markov in the 19th century. He showed that the Lagrange spectrum begins discrete in the sense that it has a smaller element, square root of 5, a second smaller element, which is 2 square root of 2, a third smaller element, and so on. But it's not discrete all the time. Well, but still related to this beginning of the set, we may describe exactly which are these smallest elements of the Lagrange spectrum. All the numbers of the form square root of 9 minus 4 over z square, where z is a positive integer which appears in a solution of Markov's equation, which is this Diophantine equation. X squared plus y squared plus z squared is 3xyz. And all the solutions for this equation are in this tree. So if you have a solution x, y, z, it gives birth of two new larger solutions, yz, 3yz minus x, and xz, 3xz minus y. We begin with the simplest solution, 1, 1, 1, and then we apply these operations. And this gives a tree which contains all the solutions of this equation. And an important open problem by Frobenius, has more than a century, is to determine whether the value of z, so the largest entry in a triple, determines or not the triple. So the question is whether some value of z can appear in two different places in this tree, and it's not known. It has some consequences on the pre-image of the first elements of the Lagrange spectrum by this function k. So yes, it means that the pre-image of any point in the beginning of the Lagrange spectrum in this discrete set is only one class of equivalence of rational numbers by this equivalent relation. But let's move on. So on the other direction, Marshall-Hall gave indeed the first non-trivial example of a regular Cantor set such that the arithmetic sum of this set with itself is an interval. And it's the set C4 of all numbers in 0, 1, in which continued fraction you only have coefficients 1, 2, 3, or 4. And this is a regular Cantor set in the interval 0, 1, defined by the Gauss map, which we'll introduce in a while. And Marshall-Hall proves this. But this has a consequence on the Lagrange spectrum, that the Lagrange spectrum contains a whole half-line. For instance, the half-line 6 infinity. Every number larger than 6 belongs to the Lagrange spectrum. So it begins discrete and ends as a continuous. So indeed, this largest half-line does not start at 6, but instead it starts at this nice algebraic number discovered by Feynman in 75. So all numbers between this number 4.527, etc., so larger than this number, belong to the Lagrange spectrum, and there is a gap of the Lagrange spectrum, so an interval in the complement of the Lagrange spectrum, which ends at this point. So this is the largest half line contained in the Lagrange spectrum. And all of these results, so Marshall-Hall and Feynman, are deeply related to the study of arithmetic sums of regular Cantor sets. And I will explain now what is the relation between sums of Cantor sets and the Lagrange spectrum. So sets of real numbers whose continued fraction is bounded and has some combinatorial restraints are typically regular Cantor sets defined by the restriction of the Gauss map. Gauss map is just fractionary part of 1 over x to some finite union of intervals. So you take some finite union intervals and the maximal invariant in these intervals by the Gauss map. This gives a lot of regular Cantor sets which are involved in this theory. So if you consider the continued fractional representation of a real number, you have this precise formula for k of alpha, for this best constant of approximation, which is a lim sup of alpha n plus beta n. Alpha n and beta n are continued fractions obtained from the continued fractions of alpha. Alpha n begins in an and goes through infinity, and beta n goes in backward direction beginning in an minus 1. And this formula follows from this exact formula for the error of the approximation of alpha by a conversion, so by Pn over Kn, so some rational approximation which comes from the continued fraction representation. And also from this fact that any rational approximation which is good, which has errors smaller than 1 over 2 q squared, must come from the continued fraction. So must be some convergent of the continued fraction of alpha. This together with this formula, this precise formula for the error gives, this is a very elementary formula, and gives this formula for k of alpha. But if alpha has bounded, if the coefficients an are not bounded, then k of alpha is infinity. If they are bounded, then alpha n and beta n will belong to regular Cantor sets determined defined by the Gauss map in some union of intervals, belong to some Gauss Cantor set in the sense. So this formula allows us to give a dynamical interpretation, a dynamical alternative definition of Lagrange spectrum, which is we have this real function in this shift of infinitely many symbols, so B infinity shift. We have a natural dynamics there, just the shift, so we take a sequence like this and just change the starting point. So where is the point 0? Normally it's in A0, it moves to A1, say, so this is a shift map in the symbolic space, an important abstract model for many dynamical systems. And we have this real function, which gives continued fraction to the right plus continued fraction to the left. And the set of lim sup of this function in the orbits is precisely the Lagrange spectrum. We may define the Markov spectrum, which are related sets in this way. We replace lim sup by sup. And it also has an arithmetic interpretation related to indefinite binary quadratic forms of real numbers. It's possible to prove that L and M are closed sets of real numbers, and that M contains L, so M is slightly larger than L. Well, I proved this theorem on the fractal geometry of the Lagrange spectrum. As I said, it begins discrete, it ends continuous, and in the middle it has an interesting fractal structure. For instance, given any number between 0 and 1, we may find a half line minus infinity t, whose intersection with the Lagrange spectrum has precisely this house of dimension. So the house dimension of these intersections can be any number between 0 and 1. So this function d of t measures this house of dimension. It is like a Cantor stair function in some sense, which is not Helder continuous, but it is continuous. And it gets the value 1 a little before square root of 12. And just after 3, which is the first accumulation point, the dimension gets slightly positive, so the Lagrange spectrum begins to contain small Cantor sets after 3. So in the same paper, we proved that the pre-image of large points has large house dimension which tends to 1, and that, well, you have many isolated points. If you throw out the isolated points, then you get already a perfect set. You cannot have new isolated points. Also, in collaboration with Carlos Mateus, we proved some results about the set difference between the Markov and Lagrange spectrum. As I said, it's non-empty, but it has 0 Lebesgue measure. Indeed, house of dimension smaller than 1, but positive, indeed larger than 1/2. This 0.53 is essentially the house dimension of C2, the Cantor set of points which only have 1 and 2 in the continued fraction. We also found this number, which is the largest known element in M minus L. Not in M, sorry, this is wrong. M is unbounded, M contains L. It should mean M minus L, so it's the largest known element in Markov minus Lagrange, in the Markov spectrum, but not in the Lagrange spectrum. I'm sorry. So this is a informal picture of what is known about Lagrange spectrum. So it begins this, so it has smallest elements, square root of 5, 2 square root of 2, etc. 3 is the first accumulation point. It contains this whole half-line. We don't know much, so before square root of 12, the house dimension gets 1. Square root of 13 is an isolated point. And probably even before square root of 12, it should contain small intervals, but we still cannot prove this. Probably there are also a lot of intervals between square root of 13 and the beginning of Hall's rays, but there are still many open problems on the structure of Lagrange spectrum. So the main tool from fractal geometry in order to prove this previous theorem comes from this work with Yokos. So the main technical lemma, the scale recurrence lemma, can be used in order to prove this dimension formula, which says that the house dimension of an arithmetic sum of 2 regular Cantor sets is always what we expect, provided they are not too self-similar. So at least one of the Cantor sets should be non-essentially affine. So the dynamics which define them should not be affine, at least for one of the Cantor sets. Then we always have this formula which says that the house dimension of the sum is the sum of the house dimension, or 1, no, if it's larger than 1. So Hockman and Schmerking also prove a version of this result with a completely different technique related to ergodic theory, inspired by Furstenberg. So as I said, we have these dynamical definitions of Markov and Lagrange spectra, and we may generalize this notion to a quite general setting. When we have a dynamical system, a map, and a real function, and an observable thing, we may associate to this pair a Markov spectrum and a Lagrange spectrum. Markov spectrum is the set of the supremum of the function in the orbits, and the Lagrange spectrum is the set of lim sup of the function in the orbits. So these sets only depend on the orbit space. So 2 points in the same orbit have the same image by these functions, no? The supremum and lim sup of the function in the orbit. So it kinds of measure the size of the orbit space of the dynamics. So we have this Markov and Lagrange spectra. We can do the same thing for flows. So the Markov and Lagrange spectra for flow, sup and lim sup of the function in the orbits. Okay. So here I quote some results about the structure of this Markov and Lagrange spectra. In some case, for instance, we start with a kind of dynamical systems we know more or less well. So indeed, horseshoes in the plane, so or in a surface. We have a horseshoe in a 2-dimensional manifold, so in a surface, in a typical real function, a typical horseshoe in a typical real function. Question is what the Markov and Lagrange spectra look like. And indeed, we show something related to Hall's theorem. In this case, Markov and Lagrange spectra will be bounded sets. They cannot contain rays. But we prove that if the horseshoe has dimension larger than 1, then typically the corresponding Lagrange and Markov spectra have non-empty interior. This in collaboration with Sergio Romagna from UFRJ, also my former student. And, well, we have this technical lemma, which is very important, which says that when we have a dynamics in a horseshoe in a real function, we may take the maximal invariant in a level set. So we have all points where the function is at most t, and take the maximal invariant. Then move t. We have a one-parameter family of fractal sets. And the dimensions of if you measure the stable and unstable dimensions of these sets, these dimensions depend continuously on the parameter. This is what this lemma said. And this is a version of this lemma, which depends a lot on the study of the combinatorics of the orbits. It's very important in my theorem on Markov and Lagrange, on classical Markov and Lagrange spectra. And this lemma, together with this dimension formula, which generalized the previous dimension formula, says that typically the image of a horseshoe by a real function is the minimum between 1 and the Hausdorff dimension of the horseshoe. Together with the previous lemma, we get an analogous result of this theorem of mine on the classical Lagrange and Markov spectra to typical Markov and Lagrange dynamical spectra associated to a horseshoe and to a typical real function. This is by myself, Aline Cerqueira, and Carlos Mateus. So I also proved that typically the Markov and Lagrange spectra associated to a horseshoe and to a typical real function starts with an isolated point, which is the image by the function of a periodic orbit. So this solves a question by Jean-Christophe some years ago. And with Davi Lima, also former students of mine, we proved some kind of phase transition. So the soup of the points where the dimension is smaller than 1 coincides with the infimum of the interior of this Markov and Lagrange spectra for typical pairs. So horseshoe and typical real function. So with no gap in the middle. So yeah, I have not much time, but if it's possible, I have a 2-minute movie on the geodesic flow of the modular surface, the quotient of the upper half plane by SL2Z or PSL2Z. So if it's possible to put the movie, a little part of it. Yes, this gives, so the classical Lagrange and Markov spectra can be interpreted as the set of maximum heights and maximum asymptotic heights of geodesics in this modular surface. So this is the case of 111, which gives the smallest element in Lagrange spectrum, which is square root of 5. Then we'll have the case of 2, which gives the second smallest element, which is 2 square root of 2. So this is just a fundamental domain, and you have a natural height function, which comes from the half plane, the usual height in the half plane. So in this fundamental domain, the maximum height of geodesics, the set of maximum height of geodesics give respectively Markov and Lagrange spectra. This is 3, 3, 3, 3, 3 corresponds to square root of 13, this large isolated point. So this is the fundamental domain, so the maximum height is larger here. Then we have this square root of 13, then we have square root of 12, which is the largest value corresponding to continuous fraction, which have only 1 and 2 in the continuous fraction. The largest possible value is square root of 12. Remember that before that, we get Hausdorff dimension 1 in the Markov and Lagrange spectra. The first 2 examples were isolated points, corresponds to the first two smallest elements in Markov and Lagrange spectra. And this corresponds to the third isolated point, the square root of 221 over 5. It corresponds to a more complicated periodic orbit, corresponding to period 2211. So the maximum height here is the third element in Lagrange spectrum. Okay, so I think this was the movie. So thank you to Pierre Arnoux and to Edmund Harris. Let me just quote a last result that says that this kind of behavior is typical not only in constant negative curvature, but also for typical manifolds in negative curvature bounded from below and from above by negative constants, and with finite volume. So in collaboration also with Sergio Romagna, we proved that typically Markov and Lagrange spectra associated to geodesic flows of these surfaces in negative curvature do have non-empty interior. And a good question is whether they contain house rays or not. In collaboration with Sergio and with Zezé Pacífico, we have analogous results for typical Lorentz flows, so typical geometric Lorentz flows, which are not exactly uniformly hyperbolic, but almost. So this singular hyperbolic systems. And so I have a lot of reference. And thank you very much. Thank you a lot for coming. Thank you very much. Thank you very much. Thank you.
Thank you very much, Gugu, for an inspiring lecture. The time is too short and you are too many to allow for individual questions now, but please speak to the orator individually after that. Thank you very much.
Thank you very much.